Hi, thanks for joining me. Today I'm going to be going over problem 2 from week 7 of the Michaelmas term Invariants puzzle competition. As always, I'll leave a link in the description below with details of the competition. Anyway, this is the problem that we have today. We have an denoting the largest prime divisor of n, where n is a natural number. So for example, a of 34, because 34 is 2 times 17, 2 and 17 are prime numbers, so a of 34 is going to be 17. And we also have this small technicality that a1 is defined to be equal to 1, because obviously 1 doesn't really have any prime factors. Okay, we want to prove that the sum from n equals 1 to infinity of 1 over n times an converges, i.e. is less than infinity. Okay, and I'll note that this thing here, or proving this thing here, is equivalent to proving that the sum from n equals 2 to infinity of 1 over n an is less than infinity. And the reason you might want to prove this is simply because you don't then have to worry about the small technicality of 1. And the reason these two things are equivalent, because obviously if this thing converges, then this thing here is smaller than this thing here, because it doesn't include the n equals 1 term. And if this thing here converges, then this thing here is precisely 1 over 1 plus this thing here, and obviously thus converges as well. Anyway, we want to prove that this thing converges, or that this thing converges, doesn't matter. So if you want to have a go at proving that it converges, pause the video now and give it a go for yourself, and I'm going to jump straight into a solution. Okay, so what I've written on the board is the thing that we have, the sum from n equals 2 to infinity of 1 over nan is equal to this double summation here. The sum from p being bigger than or equal to 2, where p is prime, so the sum of over all the primes, multiplied by the sum of n being greater than or equal to 2, for which an equals p of 1 over nan. Again, the reason these two things are the same is basically this sort of set here is the same as this thing here. So every natural number n bigger than or equal to 2 has a unique p for which an equals p, and that's where this thing here comes from. But we can sort of simplify this summation on the right hand side a bit. We can keep this p the same, the sum p being greater than or equal to 2 of p prime. Okay, and because we know that an equals p, we can just swap the p, swap an in the sum for p. So that's 1 over p, but of course p is independent of n, so I can bring it out of this first summation. 1 over p times the sum of n being greater than or equal to 2, and an equals p of 1 over n. Okay, and this thing here, I'm going to be defined to equal sp, or in fact including this 1 over p here. So sp is 1 over p times the sum from n equals 2 to infinity of the set of n for which an equals p of 1 over n. And now I claim that sp is less than 2 times p to the minus 3 over 2. Okay, it seems a bit rogue, but you'll see where this comes from in just a second. But the thing I want to point out is if I can prove this, i.e. sp is less than 2p to the minus 3 over 2 for all prime numbers p, or prime numbers, sorry, if I can prove that this thing holds for all prime numbers p, then this summation here is going to be less than the sum over p being greater than or equal to 2p prime of 2p to the minus 3 over 2. Okay, but this thing here converges, because obviously this thing here is less than or equal to the sum from n being bigger than or equal to 2 of 2n to the minus 3 over 2. So obviously in this case, we're also considering the non-primes, and this thing here converges sort of by, it's a geometric series. Okay, so this thing here is less than infinity. Okay, so if I can prove that this claim is, this thing here holds, then I'm done. So let's prove this, and the way we're going to prove this is by induction. Okay, so I've written up what we had on the whiteboard at the top, and we're going to prove the base cases first. So when p equals 2, so the first prime number, and also the second prime number, so when p equals 3. Okay, so let's look at S2. We want to show that S2 is less than 2 times 2 to the minus 3 over 2. But of course this is just 2 times 2 to the minus 1 times 2 to the minus half. These two things cancel, and this is just 1 over root 2. Okay, so we want to show that S2 is less than 1 over root 2. Well, what is S2? Well, let's just use the definition as 1 over 2. So just swapping p for 2. The sum, n being bigger than or equal to 2, for which an equals 2 of 1 over n. Okay, so it's the sum of the reciprocals of the natural numbers n, where the n has maximum prime divisor 2. But because n is bigger than or equal to 2, it follows that n must be a power of 2. Because if n isn't a power of 2, then it must have a prime divisor which isn't 2. And thus, because 2 is the smallest prime number, then n would have a prime divisor bigger than 2, so an wouldn't equal 2. Okay, so this is simply the sums of the reciprocals of the powers of 2. So this is just a half, which is out front, times 1 over 2, plus 1 over 4, plus 1 over 8, plus and so on. This thing here is just 1, so this is just a half. Okay, so S2 is a half, but clearly a half is less than root 2, 1 over root 2, sorry. And the reason for that is because this is if and only if root 2 is less than 2. Okay, and I guess if you want to make it even more precise, if and only if 2 is less than 4. Certainly 2 is less than 4, so root 2 is less than 2, and thus a half is less than 1 over root 2. So that's the case P equals 2 done. And now I'll leave it as an exercise for you to check that S3 is also less than 2 times 3 to the minus 3 over 2. Use a very similar sort of argument, except when you're considering an equals 2, you've also got to consider the numbers which have 3 in its prime expansion, but also the number 2 in it. So you're not here. We were just considering powers of 2. Of course, we've got to consider powers of 3, but we've also got to consider powers of 3 times powers of 2. Okay, so it's a bit more intricate, but you still get the same result. So those are the base cases done. Let's continue with our proof. Okay, so now what we want to prove is that S sub Pn plus 1 is less than 2Pn plus 1 to the minus 3 over 2. Okay, and before I get into looking at P sub n plus 1, let's make a generic point, so about a generic prime number. So an equals PR, so the rth prime number, where r is just some generic natural number. So an equals PR if and only if n takes the form PR times p1 to the alpha 2 times, p1 to the alpha 1 times p2 to the alpha 2 times ... all the way up to pr to the alpha r, where alpha 1, alpha 2, all the way up to alpha r are non-negative integers. Okay, well, why does this hold? Well, suppose an equals pr, well then that means that n has largest prime divisor, pr. So certainly pr divides n, so that means that n is equal to pr times something, but that something has a prime decomposition, but the prime decomposition must involve primes less than or equal to pr, because if it involved a prime number bigger than pr, then that would mean that n had a prime divisor bigger than pr, and then that would mean that an is bigger than pr. Okay, so certainly n takes this form here, and now conversely, suppose n takes the form pr times p1 to the alpha 1 times p2 to the alpha 2, and so on, then an equals pr. Okay, so this is an if and only if relationship, and the reason the converse holds is quite clear. If n equals this form here, then clearly pr divides n, and pr is the biggest prime divisor of n, because its only other prime divisors are p1, p2, all the way up to pr. Okay, so this thing holds. Now, we want to consider this thing here, the sum from n being greater than or equal to 2, for which an equals pr of 1 over n. So this is going to be precisely the sum of 1 over pr times 1 over p1 to the alpha 1 times p2 to the alpha 2 times ... all the way up to pr to the alpha r, where 0 is, alpha 1, alpha 2, ... alpha r are non-negative integers. So the set of combinations of these, well, firstly I'm going to bring up the 1 over pr to the front, because that's independent of alpha 1, alpha 2, all the way up to alpha r. So this is 1 over pr times the sum of alpha 1, alpha 2 varying over the non-negative integers of 1 over p1 to the alpha 1 times ... all the way up to 1 over pr to the alpha r. But this thing here is simply equal to the product, okay, of I being less than, between 1 and r, of 1 plus 1 over pi plus 1 over pi squared plus 1 over pi cubed plus ... all the way up to infinity. Now everything's sort of quite clear, except perhaps going from this line to this line. To show that this summation here equals this product here, you can sort of think, well, look at this product here, it's a product of a bunch of infinite sums, and if you look at those infinite sums and perhaps expand the product, you can see that every different possible combination of alpha 1, alpha 2, all the way up to alpha r will be somewhere in this expanded product. And the reason for that is if you just look at the alpha 1 term of the first element, and then multiply that by the alpha 2 term of the second element, and so on, you're going to get 1 over P1 to the alpha 1 times 1 over P2 to the alpha 2, all the way up to 1 over PR to the alpha R. And that's why this thing equals this thing, but this thing here is just a geometric series, 1 plus 1 over Pi plus 1 over Pi squared, and so on. This is precisely 1 over 1 minus 1 over Pi, and just multiplying the top and bottom by Pi, this thing here is equal to Pi over Pi minus 1. Okay, so we've written this thing here, the sum from n being bigger than or equal to 2, for which an equals PR of 1 over n, in this sort of nice product form. Let's move up to the top of the whiteboard and continue. Okay, so I've just written up the result we derived at the top of the whiteboard. Now notice, if we divide both sides by PR, so on the left hand side we now have 1 over PR times this sum here. The left hand side is precisely S sub PR. So let's just do that. Let's divide both sides by PR. So when we divide the right hand side by PR, we just get the 1 over PR now becomes 1 over PR squared. And on the left hand side we get S sub PR. And I remember R is just a generic natural number, so this holds for all natural numbers R. So S sub PR is equal to 1 over PR squared times this product here. So now what we want to do is look at S sub Pn plus 1. So S sub Pn plus 1, well that's just going to be equal to 1 over Pn plus 1 squared times this product here, so the product from 1 being less than or equal to I being less than or equal to R of P sub I all over, oh sorry not R, n plus 1 of P sub I minus 1. What I'm going to do is just take out the last element in this product, so when I equals n plus 1. So this is equal to 1 over Pn plus 1 squared times Pn plus 1 all over Pn plus 1 minus 1 times the product from I going from 1 to n, because I've taken out the last element. But when I take the product from I equals 1 to n, that's just the case 1 over Pn squared, so bringing this to the right hand side, times S sub Pn. Okay, so let me write that out in full. The product from 1 being less than I, less than or equal to n, of Pi all over Pi minus 1. But this thing here is precisely Pn squared times Spn. Okay, so Spn plus 1 is equal to Pn squared all over Pn plus 1 squared times Pn plus 1 all over Pn plus 1 minus 1 times Spn. Of course, we can cancel out one of the Pn plus 1s, so we get this thing here. So Spn plus 1 is equal to Pn squared all over Pn plus 1 times Pn plus 1 minus 1 times Spn. Now let's use this equality to derive that Spn plus 1 is less than 2 times P sub n plus 1 to the minus 3 over 2. Okay, so I've just written up what we had before at the top of the whiteboard, and I've also written this thing here. 2 times P sub n plus 1 minus 1 is less than 2 sub Pn plus 1. This is quite clear because we've got a minus 1 here, but we don't have the minus 1 there. And this thing here is less than or equal to Pn plus 1 minus Pn, all times Pn plus 1. And the reason this thing holds here is because obviously the Pn plus 1 is the same, and this here is a difference of 2 primes, and that's bigger than or equal to 2. And now you might be wondering, well, what about if we're just looking at the first 2 primes, because i.e. 3 and 2, then 3 minus 2 is 1, which obviously isn't bigger than or equal to 2. And the reason we don't have to worry about that is because we've already dealt with the base case of 2 and 3, so we're assuming that Pn plus 1 Pn is bigger than or equal to 3, and thus Pn plus 1 is Pn plus 1 are both odd primes, so their difference is going to be at least 2. Okay, so this thing here holds. If I expand out this right hand side, I get Pn plus 1 squared minus Pn plus 1 times Pn. So bringing everything onto, or bringing this 2 terms onto that side, and the Pn plus 1 and the Pn onto that side, I get that Pn plus 1 Pn is less than Pn plus 1 squared minus 2Pn plus 1 plus 1. But this thing here is just Pn plus 1 minus 1 all squared. So I get that this thing here is strictly greater than this thing here, and taking square roots on both sides, I get this inequality here. Now let's use this, plug this back into here, use our assumption to finally result in what we want. Okay, so we're at the last stage of this proof. We just showed that Pn plus 1 minus 1 is strictly greater than square root of Pn times Pn plus 1. Now what we're going to do is, well, use this. Firstly, let's invert both sides. So, and of course that flips the sign of the inequality. But of course we've got Pn plus 1 minus 1 inverse in this thing here. So we have that S sub Pn plus 1 is going to be strictly less than Pn squared all over Pn plus 1 times the square root of Pn times Pn plus 1, and then that's times by S sub Pn. And now this thing here is Pn to the 3 over 2 divided by Pn plus 1 to the 3 over 2 times Spn. But remember, Spn by assumption is less than 2 times Pn to the minus 3 over 2. So this is Pn plus 1 to the 3 over 2. And this thing, Spn, is less than 2 times Pn to the minus 3 over 2. And of course the Pn to the minus 3 over 2 and the Pn to the 3 over 2 cancel. And we're just left with 2 over Pn plus 1 to the 3 over 2, which is equal to 2 times Pn plus 1 to the minus 3 over 2. And we're done. Okay, so it's quite a nice long proof using different techniques, but it's quite a cool convergence series which uses, or to prove that it's convergent, you're not using like the ratio test or anything like that, any of the common tests. But yeah, I hope you have enjoyed this video. Finally, the solution is there, proving that it's convergent. If you are new here, please do consider subscribing and checking out some of my other fun maths videos as well. But yeah, that's all for today. I will catch you in the next one. Have a great day.